All right, good morning, grade 12s. So today we're going to go through the ins and outs of uniform circular motion. Okay, so just as an introduction here, uniform circular motion is defined as the motion of an object traveling at a constant or uniform speed on a circular path. Okay, so if we take a look at the diagram here, the object is clearly moving in a circle. Okay, that is the direction of motion. And again, we've talked about the natural tendency is an object to move in a straight line. So therefore, something must be happening to keep an object moving in a circular path, which we will be discussing later on. Okay, so a couple of things that become evident here in this diagram. The acceleration vector is always pointed towards the center of the circle. And interestingly, the velocity at any time is tangent to the circular path. So if an object was moving in a circle like this, and you snap the string right at that point, the object would move in a straight line, straight down. Okay, so as long as there's a force pulling the object towards the center, the object will move in a circular path. But more on that in a little bit. So the magnitude of the velocity remains constant. Okay, so the speed, all right, remains constant, but the direction of the velocity vector is always changing. So therefore, we have acceleration. Remember that acceleration occurs when an object speeds up, slows down, or changes direction. So a little bit then about the kinematics of circular motion. So again, as a quick review, velocity v is displacement over time. But the object moves around a circular path, just think circle. So the distance traveled must be equal to the circumference of the circular path, where the circumference c would be 2 pi times the radius, as we recall from the basic math equation. So the time taken to complete one revolution, okay, one cycle around the circle, is called the period. And remember from our waves unit in 30S physics that the period is the time taken to complete one wave cycle. So if we're going around in a circle, delta d would equal the circumference, which of course equals 2 pi times the radius. Remember, the radius is the distance from the center to the edge of the circumference of the circle. And recall that period t is the time for one cycle. Period is also the reciprocal of frequency. Remember, frequency is the number of cycles per second. So frequency is equal to 1 over the period. So those are reciprocals of each other. Okay, and it's very important to note that the period is kind of analogous to the delta t in this case. So if we put this together, recalling that velocity is delta d over delta t. Okay, if we put this together for circular motion, the velocity in this case would equal the circumference divided by the period. Okay, and so if we have a definition for circumference, 2 pi r divided by the period. Now, if period and frequency are reciprocals of each other, the first definition of the velocity in a circle, v would equal 2 pi r divided by the period. And number two, the velocity would equal 2 pi r multiplied by the frequency of the circle, of the motion in the circular path. So we have two definitions for velocity. Note at any time that the direction is always tangent to the circle, always tangent to the circle. So in other words, it's perpendicular to the radius of the circle. So we'll go through an example here, very simple example, determining the tangential speed, okay, of an object. So a ball is tied to the end of a string and whirled around in a circular path. So we draw our circular path. That looks more like an oval, but I think you get the idea. That's the center, that's the radius. So the radius is exactly 75 centimeters. So R equals 75 centimeters, which automatically you need it in meters. So 0.75 meters. The ball makes 3.5 revolutions per second. 3.5 revolutions per second. That sounds like a frequency. Remember, frequency is number of revolutions per second. If it said it takes 3.5 seconds to make one revolution, then that would be the period. So in this case, the 3.5 is frequency. It's important in these questions that you note the difference between frequency and the period. So what is the speed of the ball? Well, the speed of the ball would be equal to 2 pi r multiplied by the frequency. Okay, so notice that we're not using 3.14, we're just maintaining pi. So 2 pi times 0.75 meters times 3.5 revolutions per second. And we can plug it into the calculator. So 2 pi times 0.75 multiplied by 3.5, and that yields 16.49 meters per second. Okay, so that would be the speed of the ball moving around the circular path. So if there's the ball moving in a circular path, the speed would be 16.49 meters per second. All right. We'll discuss now centripetal acceleration. So this is a key word, centripetal. Centripetal is a word that means center seeking. And so centripetal acceleration is designated A sub c for centripetal. So again, any change in velocity, be it magnitude or direction, is the result of acceleration. So there must be a center-seeking acceleration here. And notice that the center-seeking acceleration is always pointed towards the center. So here in this diagram, if our object is right here, let's say it's moving counterclockwise, okay? At this point, then, if I drew the AC vector, it would be there. And the velocity would be tangent, so that would be the velocity. If we moved it and looked over here, the AC would be directed again towards the center, and the velocity would be tangent to the circle. And one more down here, AC would be pointed towards the center of the circle, and the velocity would be tangent. So again, the relationship, center-seeking acceleration, okay, always towards the center of the circle, and of course, velocity is always tangent. So the magnitude of the centripetal acceleration is given by the following, and we're not going to derive this. If you want to derive, look at the derivation of this, you can look in your textbook. And I'll give you a page reference. Page 107. So if you want to derive this, look on page 107. Otherwise, for grade 12 physics, we're just going to begin with the simplest definition. So centripetal acceleration, the simplest definition, is the square of the velocity divided by the radius of the circle. So that is the simplest definition for centripetal acceleration. So of course, we can define velocity as two other things. Velocity is 2 pi r times the period, or velocity is 2 pi r times the frequency. So what we can do, if we don't know what this velocity is, then we can substitute either 2 pi rt or 2 pi rf into the velocity, okay? And so I'm not going to derive this to save time, but what happens is you get three definitions for centripetal acceleration. So if we substitute 2 pi RT here, centripetal acceleration, all right, would equal 4 pi squared r divided by t squared, and that's the period squared, or the centripetal acceleration would equal 4 pi squared r times the square of the frequency. So we have three definitions for centripetal acceleration, and note that only the first one has the actual velocity in it. You would use 2 or 3 if you don't know what the speed is. So if we look at our next example, well, I kind of covered off those notes. So I'm not going to bother filling that in. I did that all there. So I didn't go through the derivation, and we don't need to know that. You just need to know equation 1, equation 2, and equation 3. All right. So we can look at an example then of centripetal acceleration. We have a grinding wheel. Okay, so the grinding wheels spin really fast. 5,500 RPM. RPM is revolutions per minute. Okay, so we need that in revolutions per second. Okay, so we'll deal with that in a second here. So the bottom line is the conversion to go from RPM to RPS is you divide by 60, okay, because there's 60 seconds in a minute. So the frequency then would be 5,500 divided by 60. And we'll just leave that as a fraction. We don't really need the decimal here. We know that the radius r is 35 centimeters, which is 0.35 meters. So what we can do then here is solve for centripetal acceleration. So the centripetal acceleration then would be 4 pi squared times the r, which is 0.35 meters, times 5,500 divided by 60 squared. So we can plug all that into our calculator in one step, and we can get an answer for the centripetal acceleration. So this becomes then 4 pi squared, so pi squared times 0.35 times 5,500 divided by 60 squared. And you get a large number, 116,104.9. So 116,105 meters per second squared. And if we want to take it to sig figs, I believe there has to be 2 sig figs here. So round the 1 followed by 6. So 120,000 meters per second squared. And the direction would always be towards the center. Or if we want to abbreviate TTC, so towards the center. So that would be the acceleration of this grinding wheel. And it's a large number because it's spinning very, very fast. So example 3 is just a unit conversion example. So a real life example here, the moon. So the Earth is here and the moon, okay, not to scale, literally orbits the Earth in a pretty much circular path. So we're going to calculate the acceleration of the moon towards the Earth. So we know that the radius is 385,000 kilometers. And the period is 27.3 days. And we want to find the centripetal acceleration. So because we know the period and the radius, it's going to be 4 pi squared r divided by t squared. But note, you've got units to deal with. So kilometers have to go to meters, and days have to go to seconds. So that is the work here, is doing the conversions. I'll leave you with the answer, and you can work on this on your own, you should get a very small number, 2.73 times 10 to the negative 3 meters per second squared towards Earth. So that's a good thing. We don't have to worry about the moon falling into the Earth anytime soon. So you guys can try example 3 on your own and check that you can get that answer. And I believe this takes us to the dynamics, which I will make a video on this tomorrow. So for today, I'd like you to review what we've gone through with the kinematics of circular motion. Look at this as a recap here. All right, important definitions. Number 1, tangential speed. Okay, 2 pi r divided by the period of the object moving around the circle, or 2 pi r times the frequency. We then look at the centripetal acceleration, which is always center seeking. The first definition is the square of the speed over r, radius, or the other 2 definitions we use if we don't know the speed, 4 pi squared r over t squared, and 4 pi squared r times f squared. So that is just a recap of the kinematics of circular motion, and you can refer to my website for the assignment for today.